Thank you, Fletcher. It's my pleasure to introduce Dr. John Fletcher, who's the Chief Scientist at the Innovation Game Foundation, and excited to hear from you.
Hi, everybody. It's good to be here. My name's John Fletcher. What the slides don't. Oh, okay. And I'm going to talk about DeSci and the decline of state-funded research. This has become quite topical, of course, with Elon Musk trying to and other people trying to cut government funding in America in particular, and how this is related to reinforcement learning. So I don't think it's too much of a stretch. A lot of people know what an impact AI is going to have on science. So hopefully it will speak to itself. But also, when I talk about reinforcement learning and AI and algorithms, it's really just an example of a sort of something, I think, which you can go from beginning to end, create something which is sort of self-funding, sustainable, decentralized ecosystem for a subset of science, albeit an extremely important one, which is computational science. And then the idea is that if you can do it for one subset of science, there's no reason why you can't do it for science in general. But it is, of course, an extremely important subset, and because it includes a sort of very fundamental elements of artificial intelligence, you could argue that it sort of touches every part of science. But just bear that in mind. So I just want to quickly, some of you might already be familiar with this, different types of machine learning. The reason why we're about to have a very fast acceleration in artificial intelligence, and also the type of artificial intelligence which helps with science, is because they've really got reinforcement learning going very well. This is the most powerful type of machine learning. We've all been pretty amazed by AI and how well it works so far, but I assure you haven't really seen anything yet, because previously it's been supervised and unsupervised. Unsupervised learning is just when you sort of stuff a load of data and it tries to do a next token prediction. So if you, I don't know, give it thousands of pictures of cats or something, and you wanted to do some sort of in-painting on a paint shop, and you sort of chop the cat's head off, it will probably be able to give you a sort of plausible cat's head to reproduce it, because it knows the patterns, it knows the correlations. But if you gave it a load of nonsense, like a load of pictures of headless cats or something, then it wouldn't know the difference. It doesn't know what a headless cat is. It doesn't know the difference between know that it sort of looks wrong in some way. It just sort of spews out whatever you put in. Supervised learning is sort of made famous, I guess, by labeled data, and this is largely what things like ChatGPT have been built on. People kind of asking it questions and it knowing the answer. But reinforcement learning is a bit more like how humans learn, or kind of really the most powerful way that they learn. There's some kind of reward, and they experiment. And then if there's something they don't understand, they'll play around in that particular area where their understanding is sort of lacking, and sort of focus on learning and build up the gaps in their understanding that way. So it really is a very an amazing thing, and nobody really knew how to do it for the current AI models until they started looking at so-called chains of thought, where you feed the prompts back in, or the kind of outputs back in as prompts, and then they realized it sort of enabled a type of reinforcement learning. But strangely enough, it works best for certain types of problems, problems that have a very well-defined answer, and problems where the answer is very efficiently checkable. So if you think not everything is like this, I mean, if you build a building, I suppose you could sort of see if it falls down, but that's kind of extreme. How do you know that you've done it right? There's not a sort of quick and easy check. But if you, for example, I'm trying to think of a non-mathematical example. If you sort of play a game of chess, for example, you get a sort of right or wrong answer at the end. You lose or you win. Or a bit more kind of exotically, if you try and solve the traveling salesman problem. Someone tells you the way out of a maze. This might be a good one. It's hard to find a way out of a maze, but if you tell somebody else how you found your way out, they just have to go one route. They check, they find their way out, and it's very efficient. And these kind of problems are all over the place in science and technology. In fact, I would argue that all of the most important problems in science and mathematics really have this structure of being hard to solve but easy to verify. And that means they're getting very, very far with reinforcement learning very quickly. So this is just an example of it. This guy called Terence Tao, he's probably the most famous living mathematician, and he tried to create a fiendishly difficult set of mathematics problems, which he said, in fact, would take professional mathematicians like him, which is a very high standard, probably days to solve some of these problems. And they just sort of wanted this as a benchmark, and some AIs had a go, and they really did terribly. And then he thought it would take years, and then just a couple of months later, O3, which was trained using reinforcement learning, got 25% on this exam. And probably by the end of the year, I would predict that the most most capable mathematician in the world will be a computer, which is a very strange thought. Of course, we've gotten used to the idea of the best chess player in the world being a computer and the best Go player. As of relatively recently, I'm pretty sure the best mathematician will be a computer too. And this is sort of really quite a lot more impact. I mean, it's very impressive getting a computer to play Go and chess, but fundamentally, buildings and spacecraft and drugs are not built with chess and Go, but they are built, fundamentally on kind of mathematical principles. So this will have a great acceleration of science and also acceleration of AI itself, because things like backpropagation, the attention mechanism, they're sort of fundamental algorithmic mathematical techniques which the AI will be able to self-improve. Not necessarily in this kind of intelligence explosion way, although it may do, but it's just going to be increasingly helpful to mathematicians and scientists in telling them what to try first and which directions to look at. So this is one of the reasons we're going to have a huge acceleration. As I said, this is important for sort of fundamentally asymmetric problems and other things for which reinforcement learning really works the best. You might think this is a subset of problems. If you think kind of mathematical generality, it is. But when you think of science problems, like important scientific challenges, they really are either all like that, or they can be transformed into a problem of that type. Or they're things, you've heard of this concept of an inverse problem. Some people would, in fact, say, I think probably got quite a lot of truth to it, that science itself is an inverse problem. You're not sort of given the answer, and then you're sort of asked to figure out the consequences of that. What you're given is a sort of a load of consequences, and you're asked to figure out the sort of underlying mechanisms which led to those consequences. So in a sense, it's going backwards in time. You're given the sort of output of a sensor, and then you're wondering, what happened earlier in time when this output was interacting with the object of interest. So it's trying to sort of reverse time, which is a very difficult thing to do, but computers can do it, and they can do it. Ultimately, they'll be able to do it a lot better than human beings. And so just one kind of interesting example is, there's a lot of simulations in science. But if you think about it, simulations are not easy to verify, but in fact, simulations are not really what scientists want to do. Some of them think they are. But in fact, what they want to do is solve the inverse problem, and they're often using a computer to do a simulation. They're tweaking it a little bit, so they're solving an inverse problem, but it's the man and the machine put together, a sort of hybrid system. And of course, the man is ultimately going to be the bottleneck in that system. And so people don't really want to do simulations. They normally want to do sort of inversions. So they don't normally want to simulate what happens, in a racing car with a wing of a particular shape. What they want to know is, what shape should I make the wing in order for a particular thing to happen? And that problem, mathematically, is efficiently verifiable. So that's just to say that it really is a very rich and important class of problems. So this is just a little bit to confirm that sort of algorithmic methods. A lot of talk in AI is about hardware and also data. Those things are, of course, are extremely important, but ultimately a computer will create its own data through simulations. Once you understand the underlying mechanisms, you can simulate things very accurately. The red line here is it's not very easy to read. This is how fast hardware has improved effective compute over several decades. And this is an exponential scale, so this is really, this is the doubling of Moore's law. But the blue line is what algorithms have done. So they've outstripped hardware, and they're just going to take off, leave hardware essentially in the dust. And so there's an interesting reason why people talk about hardware a lot. It's because you can just throw money at it, and you can make progress without having to innovate, which is always the hardest thing to do. Just buy more and more GPUs and sort of brute force and outspend your rivals. But interestingly, this guy relatively recently made our job a little bit more interesting. It was very hard to tell the man on the street that hardware wasn't the most important thing. Then he invented a better algorithm. But we already know this from the attention mechanism, and the transformer was an algorithmic method. It wasn't a breakthrough in hardware, which led to the current AI revolution, and this was another 57x leap in a single day because of somebody invented something, a clever algorithmic method. And if you think about that, how long does that means you can train a model with 20 times less power. And how often does the battery life on your iPhone increase by 20x from one generation to another? Never, and that's because hardware moves so much slowly and is so much less powerful than algorithmic methods. So basically, we're going to have computers generating their own algorithmic methods, and these are going to be deployed across AI and across all of science, which might sound fantastic, but the danger of that is really centralization. So when you have a sort of profit motive, private companies, of course, can do a thing, they can sell it. But for all its faults, government funding of science over the years has tended to meant that the output is published openly. And that's because it's public money, and this is part of the deal. But if you can do all this science profitably, and even basic level, low-level fundamental science, the game theory means that you're incentivized to keep it closed. So you have to think about incentives, and that's what we've been doing at the innovation game. Now, I'm sort of running out of time here, so I'll skip over this quite quickly. But what the innovation game does, really, the secret sauce is it creates a synthetic source of demand, who are really people, proof-of-work miners. They use algorithms to mine faster, so they don't even necessarily care about what they do or care about science in general, but they'll always want to mine more efficiently for profit. So the algorithms that they use, and the ones that are most successful, are just used as a market signal to know which ones to remunerate. And that's the key. With a lot of science, because you don't have a precise metric a lot of the time, it's hard to know who to give money to, who not to give money to. Maybe you give money to some guy who's 60 years old because he won a Nobel Prize for something that he did when he was 20 years old, and now he's not so good, but now he still gets the funding. So, but the thing is, if you look at Formula One racing, you don't have, these kind of like old, Sterling Moss and stuff driving around. And that's the reason, because you can tell there's an objective criterion by which they're better or they're worse. And if you're racing to solve these proof-of-work puzzles, it means that you only give out rewards for things which have already succeeded. So one thing to highlight about this is it's not fundraising. It's really just a continuous prize which is offered for anyone who gets to the top of this leaderboard. And so how are they going to fund it? Well, they can fund their research by traditional methods, asking investors for money for their research. And the investment case, at least in computational science, can involve, if we get to the top of this leaderboard, we get a return. So this is a sort of an additional source of revenue for people who find algorithms which are important in science and technology. And essentially what it does is it makes the activity privately investable, whereas it wasn't before. And if you don't understand exactly why that is, I think you have to come and find me later, because I haven't got time to go into the nuances now, but it is quite interesting. So with that, I think I've run out of time, and please check us out online and on Twitter.